Have you ever just hit a wall in a math problem? One of those equations that just feels completely impossible to solve? Well, that's exactly what we're diving into today. The story of how some mathematicians got so stuck they solved an impossible problem not by finding a new rule, but by inventing a whole new kind of number. So let's start with a question. Just think about this for a second. What number times itself gives you -9? Okay, well, let's try 3. 3 times 3 is +9. Nope. What about -3? Well, a negative times a negative is a positive, so -3 times -3 is also +9. It feels like there's just no answer, right? And you know what? In the world of numbers we use every single day, what mathematicians call real numbers, this equation literally has no solution. It's a total brick wall. But in mathematics, when you hit a wall, you don't just turn around. You start looking for a door. For centuries, this was just seen as an impossible equation. It was this frustrating little dead end that kept popping up in more and more complicated problems, basically signaling that a piece of the puzzle was missing. Something wasn't right with their mathematical toolkit. And this is where math gets really, really cool. Because when the rules you have can't solve your problem, you don't just give up. You expand the system. You invent new rules. You change the game. So, to solve this puzzle, mathematicians did something incredibly bold. They decided to invent a brand new number, a number whose entire purpose, its reason for being, was to do the one thing no other number could, give a negative result when you square it. And here it is, the hero of our story, the number I. Now, it was actually named imaginary, almost as an insult, because it just seemed so abstract and made up. But its definition is unbelievably powerful. By definition, I is the square root of -1. This one little idea is the key that unlocks everything. And this right here, this is the foundation for a whole new branch of math. If I is the square root of -1, then it has to be true that I squared is -1. This is the single most important rule you need to remember. Everything else follows from this. So let's circle all the way back to our original problem. How does I fix it? Well, we can now think of the square root of -9 as two pieces. The square root of 9 times the square root of -1. We know the square root of 9 is 3, and we just defined the square root of -1 as I. So you put them together and bam, the answer is plus or minus 3I. Suddenly, the impossible becomes possible. Okay, so we've got this powerful new tool in our belt. But like any tool, you've got to know how to use it, right? Well, the good news is the rules are surprisingly simple. Seriously, there are only two things you really, really need to remember. First, when you're adding, subtracting, or multiplying, just treat I like you would any other variable, like an x. And second, this is the magic trick, anytime an I squared pops up in your work, you immediately swap it out and replace it with a -1. That's it. That's the whole game. Now, when we take one of our normal, real numbers and combine it with one of these new imaginary numbers, we get something called a complex number. It's got two parts. The A is the real part we're all used to, and the BI is the new imaginary part. This is huge because it lets us think of numbers not just as points on a line, but as points anywhere on a two-dimensional map. It opens up a whole new world. Let's see this in action really quick. How would we simplify 5 times the square root of -100? Well, the first thing we do is deal with that negative inside the root. We can pull it out as the square root of -1. So now we've got 5 times the square root of 100 times the square root of -1. We know the square root of 100 is just 10, and we know our new friend, the square root of -1, is I. So all we have left is 5 times 10 times I, which is just 50I. See? Not so bad? All right, basics are down, let's level up. We can now use complex numbers to solve equations that look way more intimidating. Equations that, before today, were totally unsolvable. Take a look at this function. Finding the zeros is really just a fancy way of asking what value of x can I plug in to make this whole thing equal 0. Now, at first glance, it doesn't look like it has anything to do with imaginary numbers. But just wait. So first step, we set the whole thing equal to 0. To get started, we want to move that constant, the 34, over to the other side. So we just subtract it from both sides. That gives us x squared plus 6x equals -34. Easy enough. Now for a classic algebra move called completing the square. The whole goal here is to add a specific number to both sides that lets us factor the left side into a perfect little square term. In this case, that magic number is 9. When we add it to both sides, the left side neatly tidies up into x plus 3 squared. But look what happened on the right. We have negative 34 plus 9, which is negative 25. And we're right back to our original problem. A squared number equals a negative. But this time, we're not stuck. We have the tool for this. We can just take the square root of both sides. On the left, we get a simple x plus 3. And on the right, we get plus or minus the square root of negative 25. This is exactly where I comes to the rescue. We know the square root of 25 is 5, so the square root of negative 25 has to be 5i. Our equation is now just x plus 3 equals plus or minus 5i. The final step is to subtract 3 from both sides, and there we have it. Our two complex answers, x equals negative 3 plus 5i and negative 3 minus 5i. We just solved the unsolvable. All right, there's one more useful tool to add to our kit when we're working with these numbers, and it's called the complex conjugate. Now, I know it sounds really complicated, but I promise this is probably the easiest thing we're going to talk about. To find the complex conjugate of a number, you just find the imaginary part and you flip its sign. That is it. The real part stays exactly the same. Let's look at a few examples. For a standard a plus b, the conjugate is just a minus b. Easy. Now for 8i minus 3, remember the rule is to only change the sign of the imaginary part. So the real part, that negative 3, stays the same. We just flip the plus 8i to a negative 8i, giving us negative 8i minus 3. And if a number is purely imaginary, like negative 9i, you just flip its sign to get plus 9i. So why do we care about this? Well, this opposite number has a really neat trick. When you multiply a complex number by its conjugate, all the i's magically disappear, and you're left with a plain old real number. This is an absolute game changer when you have to divide complex numbers or simplify really messy fractions. And that kind of brings us full circle. The number I started its life as a mathematical trick, something that felt so fake they literally called it imaginary. But today, it's essential for solving very real-world problems in electrical engineering, in signal processing, and quantum mechanics. It proves that sometimes the most practical solutions come from daring to imagine the impossible. So it makes you wonder, what other problems could we solve if we were just willing to invent a new way of looking at them?